How are you all doing this morning?
Doing good.
Cool deal. Well, we're going to finish up our beta multiplier reference circuit today and try to chain everything together and see how it performs. And that's it for today, because I have a whole bunch of senior design stuff that I'm way behind on grading, and I'm sure you guys are well aware of that because most of you are in that class. So I'm going to try to get that finished up today so that you can start working on your stuff for next week. All right, so let me open up my library. And as you can probably see, I was playing around with the idea, as we had discussed on Tuesday, of making a wide metal 2 run between the drain of transistor 4 and the drain of transistor 2. So I'm going to go ahead and effectively finish that up. Once I make sure I have the right thing selected, which is taking, there we go. So the reason why I'm doing this is twofold. As we discussed the other day, by doing something like this, I'm significantly decreasing the resistance that's seen between the drain of these two transistors. And another reason to do this, hold on, is that I only had one point of contact. So there was only one via effectively on each side connected to the drain of transistor 4 and the drain of transistor 2. And so what that means is that if potentially things overheated, I could melt that single point of contact and I would no longer be able to send signals. Now I'll have 4 points of contact. And so I have effectively included some redundancy.
What were the dimensions of that part?
22 in the X and 4 in the Y. And I am presently trying to select that metal, and I'm going to make the extension go away so that it doesn't effectively put a big capacitor over M4. Move that over one, and it looks like I need to move this guy over one as well. And I'm gonna hit F5 and no error. So it's perfectly happy with me putting that large run there. Just a second. While we are at this, we still need to connect the source of M4, the source of M3, and the source of MSU2 to our VDD. And so I'm going to do something similar there. So I'm going to have, I'm just clicking or attempting to click this guy and putting a wire. And I'm going to make this guy significantly larger. Let's try 26 with no extension. That was a little too big. Okay, so 22, so the same size as the other one that we just did. And hit F5, 3 errors. Let's see what these errors are. I may be too close to the poly. Metal 1 overlaps metal 1. So the issue that it's having is that it's claiming to be not connected. So let me undo. Before I start messing with the size, no errors, all right. No errors. Okay, so for whatever reason, it didn't think it was connected earlier. Now it is. All right, and lastly, way over here, I need to connect from metal to metal. All right, so this topmost guard ring is going to be tied to VDD. And we'll circle back around to just putting a large bus section in there momentarily. All right, so we have transistors MSU2, M3, and M4 completed. So all of our PMOSs are taken care of. For NMOS, we have M2 done, where we have tied our source to our body with this big chunk down here. So let's look at M1 next. So that's our N by 2 NMOS. Text larger, rotating it 90 degrees, moving it down, and I need to set the spice model. NMOS transistor, so I need N active. Some labels on here just to remind myself of what's what. So I'll have this guy be our source. This guy be our drain. All right, so now let's look at some things. So the drain and gate of this guy are tied together. errors. I think it's because that poly, there's that little notch. Let me see what other errors. So I think that error means I'm going to have to move this guy out some. Notch. All right, so let's see what happens with this guy selected, and I make it 4 with no extension, or 5 with no extension. That got rid of all the errors. All right, now just for the sake of argument, could I move this guy closer? Still no errors. All right, I think that's as close as I could get it. So my source, excuse me, my drain and my gate are connected. This should be connected to the gate of transistor M2. So that means I'm going to have to go over the guard ring and over the guard ring that's tying this guy to ground, which I'm going to work on in a second. So that's okay. My source is going to be tied to my ground, so that's no issue. All right. Let's see, measurement. Scroll in first. $42. So I'm going to make it 45. So that would be a P-well connection. X value 45. And before I proceed, let me see, no errors. Okay. All right, so my source should be tied to my ground. Let's make it 9. All right. So I've got my source of transistor M1 tied to what's going to be my ground, so that's okay. I need my drain gate connection to be tied to the gate of transistor M2. So I'm going to need to do that using, so notice that my gate connection on transistor M2 is down here. So I'm effectively just going to flip what I've done right here. So I'm going to move this guy down here, delete this little stub. And 5 and no overlap. No error. Since I'm going to have to go over the guard rings, I'm going to need to go to my metal 2 layer. I definitely don't want that to be poly. All right, let me go ahead and put in this guy. So errors. I want to see actually how close I can put this transistor to the other one before it gives me an error, because my metal layers are too close and they're going to be at different potentials. All right, so that's no error. All right, so it looks like we have transistor M1 taken care of. So now let's work on MSU3. Which is a 20 by 2. Slice model. Copy of it. All right, so gates are going to be tied together. Source is going to be tied together. Or let's see, which one do I want to use as my source? Use the middle one as the source. These guys are going to be my drain. The drain is connected to the gate of our PMOS transistors. And the gate of this guy is connected to the gate of MSU2. I'm gonna have to come out of this. So this gate here is going to be connected here. The source is going to be connected to this node, or the gate of M1 and M2. And the drain, this guy, is going to be connected to the gate of this transistor. So I'm thinking about logistically how we're going to run all of these connections. And it may make more sense to flip the gate, or excuse me, flip the source and the drain of MSU2. And so what I mean by that is if we're trying to connect this metal to this gate, we're going to be doing some routing in this area where we're going to be going past this metal connection, which is going to short those things out. If we wanted to tie our gate to the gate, if it were over here, I think we could do that reasonably easily. So delete this guy, move this way back over here. And I feel like so let's start here, no errors. I'm gonna move this guy out of the way for a second because it's driving me nuts. It's 27 errors because this guy isn't where it's supposed to be. No errors, okay. So I moved my gate connection over there. So let's go ahead and tie these guys together here and put my so what I'm going to try to do is just copy this guy and see if it'll work. No overlap. Errors. Saying that they overlap each other, so it didn't copy my connections. That's okay. Easily rectified. Now no errors, okay. I'm thinking so if I run this out here, put a contact. Okay. It's mad that these guys aren't connected. So this is the contact that I'm going to use to run a metal 2 lead out this way to connect the gate of MSU3 to the gate drain connection of MSU2. Okay. So how close can I get this before I get an error? There. That's how close. All right. Let's make this guy 50 now. This guy also 50. All right. Let me fix what I screwed up when I moved that around when I wasn't supposed to. There we go. Apparently I'd already had a metal 2 connection there, so that's good. "23 errors, but it's because I moved this out of the way, I hope. Yeah. All right, so we have our gate connection made. I thought, oh. All right, so we have our gate connection made. Now let's do our drain connection. And so the drain of this guy should be tied to the gate of this guy, which means I'm going to come over here, move that out of the way so it's not a pain in my butt. Five with no extension. No errors, okay. Hold on just a second. So when I connect these two, I need to select this guy and tell it to not overlap because that's making it touch the source. No, neither end. Let's check this. No errors. I'm just trying to think. That poly for my gate is running underneath that metal 1 connection from the drain on the left-hand side. And then that metal 1 is tied up to metal 2, which will allow me to jump this guy across. Why is it using? So that is my drain from MSU 3 to the gates of M3 and M4. All right, so then I need to tie the source of MSU 3 to the gate drain connection of 1, which is this node down here. So I can just run, let's see. That's going to tie to that. And metal 2. 3 errors. That's left over from when it accidentally did it with metal. Let's see. No errors. All right, and then that source also needs to be tied All right, So let me think about this. We're looking at MSU1. Okay, so yeah, the source of this guy needs to be tied to our body connection, which is this guy here. So we're good there. All right, so that appears to be everything that needs to happen for MSU3, all of our connections made. I just want to double check things. The gate of MSU3 is tied to the gate of MSU2, that's this guy. The drain of MSU3 is tied to the gate of M3 and M4, that's this guy bridging this gap. Then the source of MSU3 is tied to the drain and the gate of M1. So here's our source. Here is our drain gate connection. So all that seems legit. So the last thing we have then is MSU1, which is a 10 by 2. And Moss. Rotated by 90. Spice model. And Moss. Oh, this was supposed to be 10. All right, so another time to kind of think about how our connections are going to be made. So the drain of MSU1 is tied to the drain and the gate of MSU2, which is right up here. So that's actually good. So it makes way more sense that we moved that connection, the drain to the left, although that does remind me that I didn't connect my source, but no, that's that. All right. And then our source is tied to ground, which is our gourd ring. So I'm going to call this guy the drain. This guy, the source. And the gate of this guy is tied to the gate of M1 and the gate of M2, which is this metal 2 run right here. So that should be easy enough to do. The source is going to be tied to ground, which is just going to be a guard ring around it. And we're going to ground that out. And then the drain is tied up there. All right, so let's go ahead and put our ring. to, let's see, what are the dimensions of this guy? This ring might be on 45, so let's try 40 over here. P well. So close to making it symmetrical. All right, no errors. So let's see. Here. Too close to each other. I can't do a metal 2 connection because I don't have the metal 2 run. Right, so no errors there. Okay, so the gate is tied to the M1 and M2, so that's correct. Our source. It's tied to where it needs to be tied. So now we just have our drain connection to be made. No errors. All right. So I think we have all of our transistors done. Does anybody see any egregious errors or anything that are jumping out at you with regards to the connections that I've made? I hear nobody talking. Okay.
Seems good to me. I don't see any issues.
Okay. So then we need to put in our resistor. Let's see. This resistor is tied to the source of M2. I'm going to orient it vertically in a moment. And would we say 14K? Is that right?
Yeah, that sounds correct.
All right. Sorry, what I'm thinking about now, no, that'll work, that'll work. I don't want to change the size of the resistor. I want to change the size of this piece of metal. All right, so let's make a measurement. How long is this whole thing? Somewhere in the ballpark of 227. All right. So what I'm going to do, so I'm going to put a pure piece of metal 1 up here, and I'm going to make it 250 in the X direction and 25 in the Y. And its purpose is to just be a common, effectively like a bus rail for this whole thing. That's where VDD is going to be connected. Let me see if I have any errors. No. And instead of having one little metal wire there, I don't want the node, I want the strip. So that's me tying all of that to what will be. So I'm going to export this pin as VDD. Scroll way in so I can see it and make it larger. And I'm going to take that big metal chunk and I'm going to put another one down here at the bottom. And that's going to be our ground. I'm going to tie this like so. And then this guy needs to be tied down here. I believe its width is 45. And I'm making these runs really, really wide to minimize the resistance getting down to the bottom of the circuit. No, I don't want the pin. F5, no errors. And I'm going to export this pin as ground. GND. All right. So I believe we have successfully designed the layout for our beta multiplier circuit. So let's test this by putting in some spice code. The only thing that we're going to have, it's going to be multi-line. We're going to define VDD as the voltage between node VDD and 0. It's a DC voltage source having a value of 5. We need to run, let's say, a transient analysis for 5 milliseconds. And we need to include click trick c5 models.txt. This should be, I guess, now that I think about it, that's not underscore. The exact same spice code on our schematic. So I'm just going to pop over to that and check it real quick. Yeah. Except that it's so tiny, I can't find it. There it is. All right, so just for the sake, no errors, run a well check, 3 errors. So what is it saying? Short circuit between well contacts. So it is claiming that my well connection for M1 is shorted out to my well connection for M2, but I don't see how. Anybody see anything jumping out at them? Let's see what's next. Tools. 3 years. All right, so we got that one. Short circuit. No P well contact. This area. Why is it saying that when this is our P well contact? So it's telling me I don't have a body connection, but I most obviously do. Well, let's simulate it and see what happens. No. So we want to be looking at our export signal, which is V bias P, which we're gonna have to find in all of this stuff. 3.9, 2 volts, and let's look at V bias N. Around 0.9 volts. Okay, so our layout is actually giving us a little more headroom than our schematic. Let's run the, let me make this smaller. So here's our layout one. I'm going to delete V bias N from both of them for a minute. So we've got roughly 40 millivolts of difference between these two. On the left is our layout view. On the right is our schematic view. Now the issue here per se is that if we put that 3.92 volts on our current mirror, we're probably not going to be getting 20 microamps. So it's not, the difference between these two isn't by any stretch of the imagination unreasonable. We have all those parasitics that are going to change some values a little bit. Let's see. All right. So I'm going to save my work. And I'm going to go into the Cascode Current Mirror schematic. And I'm going to comment out the VGG2 line. And I'm likely going to need to move this. I'm going to put in my beta multiplier reference. And I've tied that there. I don't need my VDD. I will need my VDS4 line. All right, so hold on, let's see. Need that one. I will need that one. I will need that one. I will need that one. Apply. Now I gotta remember what I'm supposed to be looking at through this one. So the current through M1 and the current through M2. Drain current for M1. Drain current for M2. So from the schematic standpoint, biasing our current mirror with our beta multiplier is doing exactly what it's supposed to be doing. So that's good news. Now let's see what happens with our okay, so we don't need that, or no, sorry, we do need that. We don't need this. We do need this, this, this. Move all this crap over here. Our beta multiplier layout. Drop this in. It's going to be much larger. So let's see. Where am I applying VGG to? To this guy? It's the gate of the PMOS, right?
Yeah, that's what I had. It was on the gate of the PMOS.
All right, so out of the way. Components. I'll need that in a second. Actually, I'll do that in a second because it's going to make it hard to do this. So inside my beta multiplier, I need to be able to do metal 2. So let's see, components. All right. Okay, so let's see what happens here. I'm telling it to run two different analyses and it's not liking that. I need to go into my data multiplier thing and comment out this whole thing. We're looking for the drain current of transistor 1, which is showing up. Well, that's it's looking like it's something on the order of 300 microamps, which is weird. And the drain current of M2. And that's also hitting 300 microamps. Which is way out of whack. Much, much higher than we need it to be. So what I'm going to do, let me delete this wire. I'm changing this value to 3.93 because that's what our layout was giving us. I just want to see what happens. Still 300. All right. So now just for a sanity check, if I change this to 3.88, still 300. So why on earth is that happening? What have we done? All right, well, let me delete this thing out of here. Okay. I'm defining VGG2, but I don't see anywhere on here where I'm actually telling it to apply it. Do you guys? I don't know what I did, I guess deleting that export.
It was on that P Silicon arc off the PMOS that you're playing with right now. You deleted it to put the metal 2 contact there.
Okay. Let's try simulation. All right, things are looking better now. Okay, so at 3.88 volts, we get pretty much spot on to 20 microamps. And if I, whoops, don't know what I just did there. Oh, I'm hitting control, not shift. All right. So I commented it out, that line of code. I'm going to drop my beta multiplier layout in again. Oh, do this. All right, so what I'm going to do, let's change this from a so right now this guy's a 14K resistor. Let's see what happens if we put a 10K in. I just want to look at what's going on with this guy. So we're trying to figure out what resistor value we need to get this guy to output 3.88. .9, so it's less. Let's try what the textbook used of 6.5K. .89. All right. Let's see what happens. Need to comment all these out. Go here. Still at 300. Still at 300. So why on earth is this guy just hitting 300 microamps regardless of what we connect to it. That's odd. So we know that our beta multiplier stage, let's see, if VGS2 is, or VGG2 is exported, let me see if we can see what voltage is actually showing up there. If we have some sort of loading effects. Just VGG2. Okay, so that explains it. So for whatever reason, when we tie these guys together, it's telling us that the voltage at the gate is 0. It's grounding it out. And what that means is if the voltage at the gate is grounded out, then for this particular PMOS transistor, it is biased like crazy deep into the saturation region, right? Because on the threshold of the saturation region is again going to be about 0.95 volts below VDD. And we're 4 volts past that. So we're deep, deep, deep in the saturation region, experiencing about as much channel length modulation as you possibly could. So that's why the current is crazy high. So why is this voltage 0? When it should be 3.88 volts. So one thing I can see, this isn't tied to that, which that shouldn't make. Let's see if that helps at all. Putting our body specifically at 5 volts. Oh, that didn't fix anything there. What is shorting out? Anybody have any thoughts? I'm at a loss currently.
Yeah, I'm not sure. I was dealing with something else that I only just now fixed. It kept when I was trying to tie the two together. It was complaining about my contact being too big, and I realized it didn't. It was already had a contact there, and it was basically just doubling the size of it for some weird reason.
So this is 5 volts. This whole region should be 5. So V bias P. All right, so why is it displaying it as a function of VDD? So what I just did, so before we were getting nothing, and now we're getting something that is swinging wildly between, well, I say it's swinging wildly, but it's actually between 4.999 and 5.000. So it's just noisy, but it's not really swinging wildly, but we're getting 5 volts there. And so what I just did is I made sure that I said that this VDD inside of this circuit specifically was 5 volts. So effectively, because I didn't have, since I had commented out the VDD thing here, it didn't treat it, this circuit, as if the power was on. So that's my mistake. I thought it would use the global variable VDD I declared in this one for all instances of VDD, and apparently that's not the case. So now we need to figure out, now that our transistor is on, why it's pulled this voltage up to 5 volts when it should be 3.88 volts. Well, while we're at it, let's just see what the current we're getting is. So with the gate drain voltage at 0, that transistor should be off. So my guess is that it should be something close to nothing, but let's just see. Yep. So picoamps. And yeah. So it's biased such that it's effectively off. Let me see. Just to make sure. So effectively what I've done now is I'm just making sure that it's using the correct models inside of there. Nope, it's still at 5 volts. Power on in both circuits. We apply 3.88 volts directly. It works. Supplying, outputting roughly 3.88 volts here. So why, when I link it to the other one, does it not treat it that way? I'm sure this is how a lot of you guys feel during your senior design project when you get all of your separate subsystems working correctly, and then when you try to link them all together, it goes to hell. I'm at a loss for why it isn't working. But our schematic is working fine. All right, well, we got 10 minutes left. I'm going to play around with the schematic bit real quick here. So if I look in our differential amplifier, okay, so we have, it's now treating our beta multiplier as being tied in We have our beta multiplier tied in here. I think. Don't want to tie PDS4 to that. Leave all those on. Just in case. All right, so let's look at this guy again real quick. So this is telling me that if I have VDD on in both, it doesn't like it, whereas I needed VDD on in both in the other one, so that's fun times. I did not mean to click the gate. All right, so that's working. Just doing sanity check type stuff. All right, now I wanted to check here. Two. Oh, let's see, 3.9. All right, so what I was checking is just making sure that our schematic is doing what it's supposed to be doing. So the our input signal, or our differential input signal, is still weirdly distorted. I have yet to figure that out. But with everything chained together, this is still behaving exactly how it's supposed to be. So that's what's blowing my mind about why the layout isn't doing what it needs to be doing, because the schematic and the layout are representative of the exact same circuit. The only change I made from the layout to the schematic was I put VSU2 as two 10 by 2 transistors in parallel as opposed to a single 20x2 transistor in the schematic. So that's something that I'm going to have to play around with over the weekend. But at least our schematic is doing what it's supposed to be doing. So we have hope there. All right, I think that's enough of me being frustrated for today. So unless you guys have anything else you want to talk about, I think we'll knock off 5 or 6 minutes early here.
When do you think you'll get the videos uploaded?
Oh, I totally forgot about all that stuff. I can do probably all of them this weekend.
Perfect. Okay. Thank you.
Yep, no problem. Just completely. I wasn't getting emails yelling at me to do it, so I forgot that I needed to do it. That's all
Not
it
a
is.
problem.
Yep, thank you. Any other questions or anything?
I'm good.
All righty. Well, you guys have a great weekend, and I will catch you on Tuesday morning.
Have a good weekend.